Okay, so today we're going to talk about measuring the dimensionality of data sets using something called the participation ratio. So measuring the dimensionality of data sets using the participation ratio. Okay, so we're interested in dimensionality, and we're going to deal with this thing called the participation ratio. Now the question is, okay, so what do we mean by dimensionality? And there are various notions of dimensionality that are going to be important and that we should disambiguate. So what do we mean? So what is dimensionality? Okay, so let's just think about it in the context of a data set. So suppose we have a two-dimensional data set. Here it is. And this is, the data sets is, let's call it feature 1, feature 2, and we're given lots of examples. Okay, and this data set would come in, it's usually some kind of a table, right? So it'll be, this is F1, this is F2. This is our data set, right? So this is, point 1, point 2, all these various points, and we've just plotted them now in 2D. So one notion of dimensionality just says how many points, how many coordinates do I need to specify every single point? So you could say, the question would be, how many coordinates to specify each point? And in our case, every point has 2 coordinates for our data. So this is something that's called the extrinsic dimensionality of a data set. Extrinsic. It's basically the dimensionality of the space the data is sitting in. Okay, so equals number of features, more or less. Okay, so for us it's 2. Okay, and that's fine. But often our data don't fill up this space uniformly. So for example, we can imagine another data set similar to the previous one. So again, we've got feature 1, feature 2. But suppose our data points were all like sitting on this line. So here is kind of the line, and they're all sitting along the line. So indeed, if we got the data set, here's our data set. F1 and F2, so it would still be there, and we would still be using 2 points to coordinate, point 1, point N. We're still using 2 points to specify every single data point, so 2 coordinates, but it looks like this data seems to be, one-dimensional. It's lying along, all the data points are lying along a line. So so extrinsic dimensionality would still equal 2. But let's say the intrinsic dimensionality, the dimensionality of the set that data occupy, should be equal to 1, right? That of the line. So this is our new. So there is kind of a notion of the intrinsic dimensionality, which is where the data actually live, versus the extrinsic dimensionality, which is, well, however many coordinates you're using to specify them. but those coordinates are, they don't have to be special, right? So suppose, in this particular case, we could have rotated the data and have it all sit on the x-axis, and then we would be using one coordinate. So somehow the extrinsic dimensionality can sometimes be a little bit arbitrary. It's just the features you're given, but those features are just reflecting that data, and that data can live on on a lower dimensional subset. And we want to try to capture that somehow, the intrinsic the actual data dimensionality. So how can we do that? Now, there are many notions of intrinsic dimensionality, and we're going to be talking today about maybe one of the simplest and the easiest to actually compute for data, which is called the participation ratio. The participation ratio. And the way the participation ratio works is it tries to find the way the variance of the data is distributed in space, and to use the distribution of those variances to come up with a notion of the intrinsic dimensionality. So it doesn't care what coordinates the data arrived in. It tries to find data-specific coordinates, data-specific directions along which the data actually lives, and to use those to define its dimensionality. So for example, going back to our data set with the points along the line, the participation ratio tries to make the observation that data seem to live, all the data variance is along a line, and to use that to say the dimensionality is 1. Whereas in a different setting, let's say we had the data was more evenly distributed, maybe we would say, okay, well, you have some variance along this direction, you have some variance along this direction, most but not all variance, and this is remaining variance. Okay, so this would go, well, PR is so maybe somewhere between 1 and 2 for this particular data set. So it's a real valued measure, so it'll give you numbers, so fractional dimensions are also possible. But that tries to use the way the variance of the data is distributed to measure dimensionality, rather than just whatever features it happens to be specified. So first, let's go look at what the expression for it is and how we compute it, and then we can try to understand some of its properties. Okay, so to compute, how do we compute it? So to compute, the first step is we need to determine the directions in space that the data occupy. So the simplest way to do this is to use PCA, which is going to find an orthogonal set of directions along which the data lie, and order them by the amount of variance. So the more variance they capture, the earlier in that list it will be. So use PCA to determine data coordinates. And this is going to give us, so let's have our data set again. So let's just say layer along here. It's going to get tired. I'm going to get tired of drawing out all those points. So this is our first PC. This is the first direction that most of the variance is along, and then an orthogonal direction that contains the remaining variance in this case because we're in 2 dimensions. Okay, so this is going to be, we're going to call this PC1, PC2. So PCA is going to give us a set of orthonormal vectors in our space ordered, and this is the important thing, ordered by the data variance they capture. And then 2, importantly, it will also give us the variances along those dimensions. So in this case, we will get the variances along each dimension. So this will be lambda 1, lambda 2, lambda n. And this is the most variance all the way to least variance. Okay, so the very first step is to just run PCA and get this vector of variances out. Once we have that, we can simply compute participation ratio. So compute PR. And PR equals, it's going to be a function of these variances that we've computed, and it's going to be the sum of the variances squared divided by the sum of the squared variances. Okay, so this is our expression for the participation ratio. Let's look at some of the properties of the participation ratio. Here's the expression for it again. So the very first property that we might notice is that it's going to be non-negative. So is greater than or equal to 0. And that's because all the variances are greater than or equal to 0. And so this is a rational function of those variances, so it's going to also be greater than or equal to 0. And in fact, the participation ratio can't be 0, because that could only happen when all the variances are 0, and in which case we would get 0 over 0. So let's just look at this case. So this would only occur, only possible if all variances but then the PR is 0 over 0. And when are the variances all 0? That's for data sets that consist of a single point. So we can either choose to ignore those situations or just assign them a PR of 0. But most of the time we don't care about such data sets anyway, because it'll be obvious if the data set consists of a single point. We'll call for non-degenerate data sets, so greater than 1 point. PR will be greater than 0. Okay? So PR is greater than or equal to 0, and actually it will be, for most of the data sets we care about, it will actually be greater than 0.